hey, you might not be real. Number 10. Simulation argument. In 2003, a Swedish philosopher named Nick Bostrom published a paper that ruined a lot of people's sleep. 13 pages in the Philosophical Quarterly, and it went like this. One of three things must be true. Either every civilization destroys itself before it gets smart enough to build realistic simulations, or every civilization that could build them decides not to, or we are almost certainly living inside one right now. That is not mysticism. It is arithmetic. If even one civilization somewhere in the future builds simulated worlds full of thinking beings and runs millions of them, then the simulated minds outnumber the real ones by such a huge margin that any given mind, including yours, is statistically likely to be simulated. The math is not complicated. It is the conclusion that is hard to sit with. Bostrom did not say we are in a simulation. He said pick which door you think is closed and defend it. Most people cannot close the first two doors without inventing reasons that sound convenient. And that is what makes the argument sticky. It does not need you to believe anything. It just needs you to do the counting. The part that keeps physicists engaged is the testability angle. If this is a simulation, then it was built, and if it was built, then it has architecture. Architecture leaves traces, maybe in the physics, maybe in the math, maybe in the limits of what we can measure. Some researchers worry about a darker possibility. If probing the system reveals something to whoever built it, they might not appreciate the attention. Others think that fear is overblown and that the smarter move is to look for evidence and deal with what we find. Either way, Bostrom did something unusual for a philosopher. He gave physicists a reason to take a strange idea into the lab. The argument has been attacked from every angle for over 20 years, and it still stands. Not because it is right, because nobody has been able to show it is wrong. Number 9. Computationalism. In 1980, philosopher John Searle sat down and imagined a man locked in a room with a book of Chinese instructions. People slide Chinese characters under the door. The man follows the book and slides answers back. He does not understand a word of Chinese, but the people outside think he does. Searle said that is what a computer does. It follows rules without understanding anything. And for 40 years, that argument blocked the idea that machines could ever really think. But here's what happened since. We built machines that play Go, write poetry, diagnose cancer, and hold conversations that fool most humans. The man in Searle's room has gotten disturbingly good at his job. Good enough that the question has flipped. It used to be, can a machine think? Now it is, how would you know if it could? Neuroscience has been chipping away from the other side. In 2024, an international consortium called Flywire published the first complete connectome of an adult fruit fly brain. 139,000 neurons, 50 million synaptic connections, every single one mapped. If you can map it, you can copy it. If you can copy it, you can run it on something else. That is the core claim of computationalism. Thinking is not about the wet hardware. It is about the pattern. Carbon, silicon, photonic circuits, it does not matter. If the pattern is right, the experience follows. Or it does not, in which case no simulation will ever produce real minds and the whole argument collapses. We do not have the answer yet, but we are building machines that will force us to confront it. Somewhere in the next few decades, an artificial system will either pass every test we throw at it or fail in a way that reveals something fundamental about consciousness. Either result changes the simulation question from thought experiment to engineering specification. Number 8. Planck scale pixelation. There is a number in physics that shows up when you try to push the laws of nature past their breaking point. It is called the Planck length. About 1.6 times 10 to the minus 35 meters. To put that in perspective, if an atom were the size of the observable universe, a Planck length would be roughly the size of a tree. Below that scale, our equations produce nonsense. Space and time stop behaving like smooth, continuous things and start looking like something else, something discrete, something that comes in chunks. If space has a smallest possible unit, then the universe has a resolution limit. And a resolution limit is exactly what you would expect from a system that computes its contents. Every digital environment from a video game to a weather model has a grid. Resolution costs processing power. No simulator builds infinite detail when finite detail does the job. Physicists have looked for the grid. Teams studied ultra-high energy cosmic rays arriving from billions of light years away, hoping to find tiny directional biases or energy limits imposed by a lattice structure. Others searched for violations of Lorentz symmetry in particle behavior. The results so far show nothing. Whatever the grid might be, it is smaller than anything we can currently probe. But the negative results are not nothing. They tell us how fine the resolution would have to be to hide from our instruments. They set boundaries on what a low-resolution simulation could get away with. There is also the rendering shortcut. Any decent simulation does not need to calculate everything everywhere all the time. It only needs full detail where an observer is paying attention. The rest can run on approximations. Games have done this for 30 years. Render what is in front of the camera. Simplify everything behind it. If our universe uses that strategy, then looking for pixels in empty space is looking in the wrong place. The evidence might only show up in the margins of extreme measurements where full resolution and approximate resolution bleed into each other. Number 7. Second law of infodynamics. In 2022, physicist Melvin Vopson at the University of Portsmouth proposed something that made the rounds in physics departments and Reddit threads alike. He suggested that information in physical systems tends to decrease over time, reaching a state of minimum information content. He called it the second law of infodynamics. The idea runs parallel to the second law of thermodynamics, which says entropy always increases. Vopson's version says the information needed to describe a system tends toward the minimum. In practical terms, nature compresses itself. If that sounds like a hard drive defragmenting itself, you are not alone. Vopson pointed to examples across physics and biology. Atomic structure favors symmetric arrangements that require less information to describe. Genetic code across species converges on patterns that minimize information storage. Even the symmetries of fundamental particles seem to follow rules that keep data lean. His argument is that a simulated universe would need exactly this kind of built-in compression. Running a cosmos is expensive. Any system processing that much data would evolve toward efficiency or crash under its own weight. Finding signs of universal compression in the actual laws of physics would be suspicious. The pushback was immediate. Critics pointed out that symmetry and efficiency show up in nature for many reasons that do not require a simulator. Natural selection produces efficient genetic code because inefficiency gets organisms killed. Physics produces symmetry because symmetric solutions are often the most stable ones. Vopson countered by proposing a lab experiment. He predicted that information stored in physical systems has a tiny but measurable mass, tied to its energy through E equals mc squared. If you could measure the mass difference between high information and low information states in a controlled system, you would have evidence that information is a fundamental physical quantity. That experiment has not been completed yet, but it is sitting there, waiting. And unlike most simulation claims, this one comes with a number you can check. Number 6. Quantum measurement. Fire a single photon at 2 slits. Do not watch which slit it goes through. It behaves like a wave, passing through both slits and creating an interference pattern on the detector behind them. Now, put a sensor on one slit to catch which path the photon takes. The interference pattern vanishes. The photon behaves like a particle. One slit, one path, no wave. That result has been confirmed thousands of times since the 1920s, and nobody fully agrees on what it means. But the surface-level reading is hard to shake. The universe seems to render detail only when something is there to register it. That comparison to a video game engine is not original. Physicists have been making it for decades, sometimes seriously, sometimes as a joke that stops being funny the longer you think about it. In 2007, Vincent Jacques and Elaine Aspect pushed the idea further with a delayed choice experiment. They let the photon pass the slits first and then decided whether to measure which path it had taken. The result matched the later decision, as if the photon's history was written after the fact. There are explanations that do not require a simulation. Decoherence theory shows how quantum possibilities collapse into definite outcomes through interaction with the environment. Many Worlds says every outcome happens, just in separate branches. These are real frameworks supported by real math. Still, the measurement problem refuses to go away cleanly. Entanglement makes it worse. Two particles separated by any distance respond to each other's measurements instantly. Bell tests since the 1980s have closed loophole after loophole, and the correlations survive every one. No hidden local variables can account for it. For physicists who study these results daily, the simulation reading is not the only explanation, but it fits the data in a way that is uncomfortable to dismiss entirely. And the experiments keep producing results that sound more like debugging reports than natural law. Number 5. Cosmological fine-tuning. There are about 25 numbers in physics that are not derived from any deeper theory. They are just what they are: the mass of the electron, the charge of a proton, the strength of gravity, the cosmological constant. Nobody knows why these numbers have the values they do. What we do know is that if you change almost any of them by a tiny amount, the universe falls apart. The gravitational constant is balanced to roughly 1 part in 10 to the 40th power. Shift it and matter either collapses into black holes immediately or disperses so fast that no stars ever form. The cosmological constant is even more extreme. It is tuned to 1 part in 10 to the 120th power. That is the most precise fine-tuning in all of physics. If it were slightly larger, the universe would have blown apart before atoms could form. If it were slightly smaller, everything would have recollapsed into a singularity. The strong nuclear force sits at a value that allows hydrogen to fuse into helium and helium into carbon inside stars. Make it 2% weaker, and fusion stops at hydrogen. No carbon, no oxygen, no water. No biology. Make it 2% stronger, and hydrogen fuses so fast that stars burn out before planets have time to form. Physicist Fred Hoyle discovered in the 1950s that carbon only exists because of a wildly improbable nuclear resonance inside stars. Before anyone found it, he predicted it had to be there because we are made of carbon. When the lab confirmed it, he called the whole setup a put-up job, a rigged deck. For simulation theorists, these numbers look like input parameters, the kind of values a designer enters before hitting run. They are not outputs of some deeper equation. They are not inevitable. They are just suspiciously, impossibly right. The standard counter is the multiverse. If there are enough universes with random constants, then one of them will hit the jackpot by accident and we happen to be in it. That is a valid logical escape, but it trades one untestable idea for another. Meanwhile, the dials sit there, perfectly set, offering no explanation for who or what tuned them. Number 4. Holographic principle. In 1972, Jacob Bekenstein was working on black holes when he discovered something that did not make physical sense. The amount of information a black hole can hold is not proportional to its volume. It is proportional to the area of its surface. Think about that for a second. A warehouse stores more stuff than a shed because it has more room inside. But a black hole stores everything on its boundary. Its interior, whatever that even means, is irrelevant. Stephen Hawking initially pushed back on Bekenstein's claim and then spent years proving it was right. That discovery cracked open a bigger idea. If a black hole encodes its information on a two-dimensional surface, then maybe all of space works the same way. Maybe what we experience as three-dimensional reality is a projection from a flat sheet of data that sits at the boundary of the observable universe. String theorists turn this into hard math. A framework called ADS/CFT showed that a universe containing gravity can be perfectly described by a lower-dimensional theory that has no gravity at all. The two descriptions match calculation for calculation. Physicists even derived a formula showing that the geometry of space emerges from how quantum bits of information are entangled with each other. Space and distance might not be fundamental. They might be byproducts of information, relationships. If you rearrange the data, you rearrange the geometry. This does not prove someone is running us on a server, but it proves that the universe has an information architecture that can be named, measured, and tested. And any system with a definable information architecture is, by definition, the kind of thing that could be computed. Number 3. It from bit. John Archibald Wheeler was not the kind of physicist you ignore. He worked with Niels Bohr on nuclear fission. He collaborated with Einstein on unified field theory. He coined the term black hole. When he said something strange, people paid attention. In 1989, Wheeler proposed that the universe is not fundamentally made of matter or energy. It is made of information. He called it from bit. Every particle, every force, every measurable quantity in physics derives its existence from binary answers. Yes or no, spin up or spin down, pass or reflect. That sounds philosophical until you realize what it implies. If the foundation of reality is information, then physical objects are secondary. They emerge from data the way an image emerges from pixels. The pixels are real, the image is a consequence. For years, the idea sat in the background of physics, a thought experiment nobody could test. Then, Rolf Landauer provided the bridge between theory and measurement. In 1961, he published a result that should have gotten more attention than it did. He proved that erasing one bit of information has a minimum thermodynamic cost. It generates heat. The amount is tiny but exact, and it is set by the temperature of the environment. In 2012, a team at the École Normale Supérieure de Lyon confirmed Landauer's prediction in the lab. They trapped a microscopic silica bead in a carefully tuned laser potential and measured the heat produced when they erased a single bit of stored information. The numbers matched the theoretical limit precisely. That experiment crossed a line. It proved that information is not abstract. It is physical. It has mass-energy equivalence. It obeys thermodynamic law. Erasing data and burning fuel follow the same rules. If the universe runs on physical bits and processing those bits costs energy, then the universe has a computational budget. It has overhead. It has thermodynamic constraints. Those are the fingerprints of a machine, not the fingerprints of an accident. Wheeler suspected it. Landauer formalized it. The Lion experiment measured it. Each step moved the idea further from philosophy and closer to engineering. Number 2. Error-correcting codes. In 2010, Sylvester James Gates was not looking for evidence of a simulation. He was doing the kind of theoretical physics that involves chalkboards full of supersymmetry equations and a lot of coffee. What he found was something he could not explain. Buried in the mathematical structure of supersymmetric equations were patterns identical to the error-correcting codes that run inside your computer right now. Not loosely similar. Identical. The same doubly even self-dual linear binary block codes that Claude Shannon developed in the 1940s to protect telephone signals from noise. Gates and his team found these codes while working with graphical structures called adding cross. These are visual maps of the relationships between particles and forces in supersymmetric physics. When they translated the mathematics into these graphs, the error-correcting code structure was sitting there, embedded in the physics like rebar inside concrete. The immediate question: why would the laws governing the deepest layer of physical reality contain the same data protection algorithms that prevent your browser from crashing when a packet gets lost? If physics were just particles bouncing off each other, there is no reason for information theory safeguards to show up in the equations. Gates has been clear that this does not prove we are inside a simulation, but he has also been honest that he cannot explain it. In a conversation about the discovery, he said something that stuck. He said he felt the way a programmer would feel if they discovered code they did not write running inside their own software. The pattern extends beyond physics. DNA uses proofreading enzymes to detect and correct copying errors during replication. Every time your cells divide, molecular machinery runs quality control on 3 billion base pairs. Error correction is not optional in biology. It is survival. If reality is computational, then error correction is not a coincidence. It is a design requirement. Any system running at that scale of complexity would need exactly the kind of safeguards Gates found woven into the mathematics of supersymmetry. The question is not whether the codes are real. They are. The question is how they got there. Number 1. Mathematical universe. In 1960, the physicist Eugene Wigner published a short essay with a title that has haunted science ever since. He called it The Unreasonable Effectiveness of Mathematics in the Natural Sciences. His question was simple. Why does math work so well at describing the universe? Why should equations invented by primates on a small rocky planet predict the behavior of quasars and quarks with perfect accuracy? Wigner had no answer. He called it a gift that we neither understand nor deserve. Decades later, cosmologist Max Tegmark proposed one. Tegmark said mathematics does not describe reality, it is reality. In his mathematical universe hypothesis, everything that exists is a mathematical structure. Particles are not described by equations, they are equations. Fields are not modeled by functions, they are functions. The distinction between the map and the territory vanishes completely. If that sounds too abstract to matter, think about what a triangle is. A triangle does not need paper or a screen to exist. Its properties, the angles, the ratios, the area formula, are true whether anyone draws it or not. Tegmark argues the universe is the same kind of object, a mathematical structure that exists because math exists, the way the number 7 exists whether or not anyone counts to it. Tegmark then proposed the computable universe hypothesis. It says the mathematical structure we live inside is defined by computable functions. The laws of physics can be expressed as step-by-step algorithms, and anything that can be expressed as an algorithm can in principle be run on a machine. That is the cleanest path from physics to simulation. You do not need to speculate about alien supercomputers or mysterious programmers. If reality is computable, then it is simulatable. End of argument. The critics are not wrong to push back. George Ellis points out the theory is essentially untestable. You cannot observe other mathematical structures from inside this one. Gödel's incompleteness theorem suggests no mathematical system can contain its own complete truth. These are real objections. But there is one thing the critics have never been able to explain away. Physics keeps getting more mathematical, not less. Every century the equations get deeper, more abstract, more detached from everyday experience, and more accurate. Particles that were predicted on paper decades before any accelerator could find them have shown up exactly where the math said they would, every single time. If the universe is math, and math is computable, then the distinction between reality and simulation may not exist. Not because someone built a machine, but because the machine was never needed. The math was always enough.